Okay, so this week's lecture is kind of a continuation of last week. It's almost like the same topic. And we're just going to continue and we're going to go through a few different methods for class prediction. So last class we talked about the k nearest neighbors and we also talked about logistic regression. We're now going to do discriminant analysis. So here's this little plot we had before where we had our kind of movie and music preference data, and then we plotted it onto two principal components dimensions, and we could see there's actually quite a bit of difference between males and females. So we set ourselves the task of, based on the preferences, can we classify males versus females? And so we had the k nearest neighbors and we had the logistic regression. So let's just see if we can draw a line across so that most of the females are on one side and the males on the other side. So let's draw this line here. And let's just say if anything's on this side, we're going to classify it as a male. And anything on this side, we're going to classify it as a female. And so that's exactly what discriminant analysis is. It's basically we draw a line to what we call get maximal separation between the classes. Based on all this training data, then we have a new observation. If it falls on one side of the line, we assign it to one class. And if it falls on the other side of the line, we assign it to a second class. So let's kind of draw a simple two-variable example here. So we have we're going to have Hammer horror movies. And then we're going to have the so-called chick flicks here. So like Sleepless in Seattle, or let's just put The Notebook here as an example, given that I'm a big fan of these chick flicks. So The Notebook is here. So we have Hammer horror and chick flicks. So we can imagine, let's do females in green. Most females are probably going to have a high rating for chick flicks and a lower rating for Hammer horror, but it's not perfect. Some females will probably hate chick flicks and love Hammer horror. So we're not going to have this perfect separation, but as per our actual data example, there is some separation here. And then finally, on the other side, we have guys, and it's kind of the opposite. And again, these preferences, there's not a perfect separation. We're going to get some error here. And then what we would do is we would draw our line here, and any new items to the left would be green or female, and any new items here we would classify as male. Okay, now let's just do a really kind of stylized example. And you know, this would be the equation of the line, so it's actually going to be x1 plus so much x2. So let's just clear this and let's do a really stylized example. We want a black. I just got two colors, red and green. And then we have this big red class here. This is going to be like almost a perfect example with a slightly smaller green class here. And we're going to set kind of, we're going to call this X bar, this is the mean. So this will be the mean of group 2. And this will be the mean of group 1. So, and this would be kind of, each item has kind of an X1 and an X2 or an X and a Y. So say we have a new item here. So we have a new item here, a new X1 and X2. If it's here, then this is probably going to be red. This is likely to be red. And we'll say that this, we'll just call it the vector X. Kind of a big bolded X is the X1 and X2. Now we would define the probability that X equals X given a certain class, Y equals K, is probably pretty high. So the probability of, the likelihood of this data given the red class is probably pretty high. But for the green class, so this would be Y equals K, let's call it just Y equals red. And the probability X equals X, given that Y is green, this is probably going to be pretty low. And we actually got a name for this. We call it the likelihood. But there's one more thing we need to think about. There's a lot more reds than there are greens. So what we could do is we could kind of, we've got the mean X bar and X bar 1. Let's make our line halfway in between here. But the fact is, we've got so many more reds that I think the line should be shifted a little bit here. And this is to do something called the prior probability. The probability that the class is red is much bigger than the probability that Y, the class, is green. You get that? There's a lot more reds, so we're liable to have a much more higher probability than there are of greens. Now, we can actually put this kind of formally. So we have what we call the likelihood. This is given our data, how, given our class, how likely is a certain vector to be red, and given our class green, how likely is a certain vector, likely to be here. And then we have our actual, what we call our priors, which is, there's just a lot of red items. So we think that red's going to be much higher than it's green. And we can actually put this into a mathematical equation. And what we can say is the probability of choosing a class. So in our example, this would be either red or green, given our data equals the likelihood of the data given the class times by the probability of the class all over this kind of the actual probability of the data. Now, what does this look like this to be to you? You should remember this from Business Stats 1 if you're a Mississippi State student. This is actually called Bayes' rule. So all we're basically doing is to find our class probabilities. We're looking at our likelihood data, and we're kind of updating it based on the size of the classes. This is our knowledge of, how likely we are to get a red versus a green. So we actually call this guy the posterior This is what we're trying to find out. We're trying to predict, you know, which class we're in. This is the data likelihood. And this is the prior probability. Here. So this is just Bayes' rule. This is kind of the probability of the data. Now, we can actually make this a little bit more useful. We can actually write this in a different format. Equals this guy, and this is just the prior. This is how we notate the prior. So this, like, if we had 70% red in our training set, this would be 0.7 times by this. This is the likelihood. Now the probability of the data, this is just the sum of all the above. So if we have kind of, let's just say we have L classes. Big K classes. And again, it's the prior times the likelihood. So just think again, this is just some kind of prior belief. In our case, it's like how many of the points we have. And this is just where our point is situated. You know, is it in the middle of the reds? Is it in the middle of the greens? And, you know, we have two classes. Well, basically our likelihood is basically, you know, the probability of my class divided by the probability of my class plus the other class. So, you know, that's kind of almost just kind of common sense there. Okay, so just a few things. We're not going to focus on the math. What the book does is it shows you, it actually kind of relates this out, saying, hey, if this is normal, a normal distribution, then it kind of shows how we kind of get the line. So there's a lot of math. Given this, there's a lot of math to find the equation of the line. So I don't need you to be able to do try and look up at the free textbook, which will give you, and the notes, which will give you a little bit more math. But I do want you to understand this, that our posterior class probability is just the multiplying of the data likelihood by the prior, and then it's just normalized by, you know, all the priors times likelihoods for all of the classes. So it's just kind of a fancy version of doing Bayes' rule. But there's a few little things I want you to think of from the notes. And those are the kind of the rules that I want you to know. So discriminant analysis basically, and I kind of put the rules kind of nicely in the slide, so I use that rather than write it. It basically creates a boundary between the classes based on the mean value of the data, and as I showed you, the class probabilities. If we have exactly the same number of items in each class, then this line is midway between the two class means. But if we saw in our example, one item has a lot more items than the other, it kind of pushes the line away for that class. We assume that both classes have equal variances. And like, here's a little example. And it shows you kind of, this is actually output by R. It will show you your dividing line, and it will kind of show you how far the points are away from your dividing line and where they're situated. So here we can see the green class, there's a few on the wrong side of the line, and we can see this shaded class, there's one that's a long way on the wrong side of the line. Then we've got 2 points just on the maybe on the wrong side of the line. This is output that we can get from R. Also note that we can we're not really going to do any examples like this, but we can utilize multiple classes. It just means on the bottom of that equation you have more than 2 classes. And you see here, this is an example of what we call multiple discriminant analysis, where we actually split into 3 different groups. And there's just one more I want to show you before we do the R, and this is quadratic discriminant analysis. Now this, what would I do if the line between the classes isn't straight, if one curves around the other? Well, basically, all this does is rather than fit this linear line, it allows us to fit a quadratic equation using the variance, and so we can actually get a smoother fit around the classes. And again, this should make it more accurate, but sometimes this will overfit. It's just too much information. It might overfit the training data. So again, we have to do a little bit of holdout validation in order to see which method works best. So quadratic discriminant analysis is more flexible, but it is prone to overfitting, and sometimes you need more data. And it's also because you don't get the equation of the line as a linear line, and you get like linear and quadratic terms trading off against each other. It's sometimes actually more difficult to relate your results and get any real world meaning from it. Okay, so that's my little kind of conceptual introduction. So now let's just go through this in R.